So this is a work in progress. With Federico Lo Bianco, Erwan Rousseau, and Frédéric Touzet. So the general problem is just describe foliations invariant by birational maps. So of course, here when I'm talking about foliation, I'm talking about singular holomorphic foliations. And already, as is implicit by the term birational maps, we are thinking of them as living on algebraic or even more projective manifolds. Manifolds or varieties, if you want. And the subject is not new. I think that one of the first results about this, at least in the 20th century, is due to Marco Brunella, who proved that NO maps preserve NO maps on P2 or C2 preserve no holomorphic foliation. And this is indeed was, I think, answering a question by Robert Moussu. I think the result dates from '96 or something like that. And at this point, we were in the beginning of what we call the birational theory of foliations. And this is a corollary of the existence of minimal models of foliations of foliated surface. After a while, at this point, it was starting to be developed a birational classification of foliations, and by the end of the century, by the 2000s, we had a complete classification. And at the same point, I think it's also around '96, when Charles Favre and Giller and Favre, Jeff Giller and Charles Favre, also proved a classification of birational maps, right? In terms of the growth of the action of the map on the cohomology of the variety. And so having these two tools at hand, Cantat and Favre, made in around 2002, made an in-depth study of birational maps preserving foliation on surface, and they gave essentially a complete and detailed classification of foliated surfaces having birational symmetry group of infinite order. And as I say, this is it uses two main tools. One is the birational classification of foliations. And also the classification of birational maps. And they put an emphasis on the classification of birational maps in order to make their study. But essentially, in dimension 2, what we had at that point was an abundance of tools, and we could choose. We had much more than what we need to prove this, to make this kind of study. And essentially, what I want to discuss now, it's our attempts to do this kind of study in higher dimensions, but for restricting ourselves most of the time for codimension 1 foliations. And we are in a situation, in the current development of the field, we are in a situation where we have not this and not even this. And so we had the tools that we use to do the study in dimension 2 broke, and want to fix and want to understand what would be the right tools to make such a study in dimension 3 or higher. And so just to try to focus and have a clear goal that we are not going to achieve, I would like to formulate a conjecture extrapolating from what we learned from this classification. Of course, a detailed classification in arbitrary dimension should be very hard to do, to accomplish, even to state. And so let's just try to summarize in one statement what they had. Is a statement which is already present in their papers, but let's formulate here as a conjecture which should hold in arbitrary dimension. So the conjecture would be, so if you have F, codimension 1, foliation on a projective manifold, and with the group of birational transformations of F of cardinality equal to infinity, then F is defined, and then F is defined by a closed rational one form with, let's state like that, and I will explain more precisely with, let's call closed, not rational, let's put algebraic one form. And I will just explain this in 1 second. But let me just remark that this is too much to hope for, so we have to refine what we understand by birational transformations, because as soon, the first difficulty that arises when we go to higher dimensional varieties is that we can do stupid things. Just start with an example in dimension 2. take a product with P1 or with a variety to infinite automorphism group, and this would give examples having this property. Just trivial action on the base and the action by the automorphism group. So we have to mod out the group of birational transformation by the group of birational transformation which fix the leaves. So let me just be a bit more precise here by what I mean by all this. So let me just say that the foliation, F foliations vanishing on F. And of course, the foliation you can think of, it has some singular set, and outside the singular set, the foliation is locally a fibration. Okay, so we are talking about here a subsheaf of the tangent sheaf formed by the vector fields which are tangent to these leaves, and the one forms which vanishing at that leaves. And so for F of codimension 1, as was explained by Nissi in the previous talk, we have a covering and we have one forms, that holomorphic one forms with zeros of codimension at least 2, and then we ask them to patch together like that. With Tij, a cocycle which will define the dual of this normal, the conormal bundle, the dual of that guy. Okay, and also we have the integrability condition, which is vacuous in dimension 2, but starts to play a role in dimension 3 or higher, which says that these forms are like that, because if they don't satisfy this integrability condition, we don't have the local picture. We don't have that the foliations is locally away from the singular points, a fibration. Okay, and then we'll say that if X is projective, then we can just take a meromorphic section or a rational section of this bundle, and we can produce, let's just call theta, a rational one form. On X such that theta restricted to Ui is a multiple of Hi omega I. And then the group of birational transformations of F is just phi, a birational transformation of X, such that phi star theta wedge theta is equal to 0. And we have a subgroup here. Indeed, it's a normal subgroup, which is the group that maps the general, one general leaf of F to itself. Since phi is just birational, it might be delicate to, and F is singular, it might be delicate to induce an action on the space of leaves, seen just as a set, not as a topological space or anything. Even that might be complicated. But anyway, we can look at a general leaf, a leaf to a general point, and it makes sense to ask it to be preserved. So this is the subgroup which preserves general leaves. Okay? And so it seems fair to say, of course, these trivial actions that we produce by considering the product of foliation with another variety will not survive to the quotient when we pass to the quotient of beer by beer fix. And this seems to be the right question to ask, saying that f is defined by a closed or rational one form or closed algebraic one form. There, the algebraic is just that. Here we are saying that to be defined by a rational form is nothing special. As I mentioned, every foliation on a projective manifold satisfies that. But if we ask this d theta to be closed, then we are saying that the transversal dynamics, if exist theta such that defining f with d theta equals to 0, then the transverse dynamics the holonomy essentially of the holonomy pseudogroup of f is model over the additive group, at least away from the polar set of f, and it says which is essentially is as simple as possible. And there, the algebraic is just saying that the dynamics will not be modeled over C+, but a finite extension of it. Or in other words, there will exist open subset, a Zariski open, and an étale covering of this Zariski open such that the pullback of a finite étale covering is defined by a closed rational one form. Just that in the coefficients I'm allowing roots or solutions of algebraic equations. So that's the content of this and this conjecture, and I would like to say a few words or something on how we are trying to approach it. Very good. So, as I mentioned in dimension 2, one of the main tools is the structure of foliations, and we have at least conjecturally a quite compelling statement about the structure of arbitrary codimension one foliations. Servo is that to and others, which says that if I have f codimension 1 foliation on a projective manifold, then one of the following holds. A, f comes from dimension 2, or f, the transverse dynamics of f is highly structured. So let me be more precise in both points. So to say that f comes from dimension 2 is the same thing as saying that there exists a map, a birational map, from X to a surface S, such that, and foliation G on S, such that F is phi star of G. So essentially, it's the simplest way to produce codimensional foliations on higher dimensional varieties. It's never simple to make this, to choose a one form satisfying these integrability conditions. The only place where it's simple is in dimension 2. And so you construct an example in dimension 2, you pull back to your variety, and you get something like that for free. And this is, I will need a little bit more space than this small piece to explain. So, but in technical terms, we say that F is transversely projective. So let me try to explain this a little bit better. I will first explain the classical version, where I think everything becomes more clear, and this is a concept that it's not particular to the case of holomorphic foliations. It exists for any foliation. So we say that foliation, let's first restrict to the case of smooth, and in the case where also this transverse structure is everywhere defined, and so we have a foliation F defined by submersions. That's always the case. If the foliation is smooth, I can always define a foliation by local submersions, Fi, Ui. And since it has codimension 1, it could take this submersion taking values on any one-dimensional space. I would choose P1. That's where the projective come. And we assume that these conditions are related by a cocycle which take values in the automorphisms of P1. So essentially what I'm saying is that among all possible submersions that we can choose to define this foliation, I'm saying that I can choose some very restricted subset. I say submersions taking value of in P1 such that over no empty intersections, they related by this. So essentially we are putting a projective structure on the leaf space of the foliation. But in the case of foliations on holomorphic varieties, on holomorphic manifolds, on complex manifolds, as already Nissin explained, if we insist in dealing with smooth foliations, we would lose P2, for instance. There is no smooth foliation on P2, so we must allow singularities. And also this is also too restrictive. We want to allow that these projective structures has singularities on some hypersurfaces. And so this concept has evolved to a singular version, which is essentially following as follows. So we say that the foliation F on a projective manifold is transversely projective if there exists P, a P1 bundle over X, H, a foliation on P such that, which is transverse to a general fiber of P, and a section, a rational section, such that sigma star of H is equal to F. So in the smooth case, what we get is P1 bundle, a foliation age which completely transverse to every fiber of P, and a holomorphic section which is transverse to the foliation age. So we drop all this transverse, complete transverse, and start to allow singularities. And so the picture we should have in mind is that here I have X, I will have some divisor, delta, I have a P1 bundle here. The foliation upstairs is completely transverse to the general fiber, but over this divisor, it is invariant and has some singularities, especially over these things. And so this is a transversely projective foliation. And so the conjecture says that, right, the foliation is either codimension 1. A codimension 1 foliation either comes from dimension 2 or the transversely dynamics is highly structured in this sense, in this very precise sense. Very good. And so what evidence we have on this? Not much. We have I have proved with Benoit Clodon, Franck Loret, and Frédéric Touzet infinitesimal version of this conjecture, but it's just about the monodromy or the holonomy representations of algebraic leaves, which says that these are in accordance with this conjecture. All the examples we know of satisfy the conjecture, of course. But we still have, I think we're still far from having the full statement. But now there is some hope of proving that, or proving part of that in dimension 3, or at least proving that for what we need in order to study that other conjecture, right? Because now we could ask, is this true for foliations with infinite birational maps? And the point is that in dimension 2, we have the following, if we look at the classification according to the Kodaira dimension, we had something very interesting. We had, when it's equal to 2, you have the general type. And when it's smaller or equal than 1, then the classification is complicated. It has several cases. Abundance does not hold. It's not predictable. But every foliation is transversely projective. So we could, if you want, to make a talk only with conjectures and no results whatsoever. Let's say that if you have F codimension 1 on X, then and cod F smaller than the dimension of X, then F comes from lower dimensions or F is transversely projective. And so if we know that this conjecture is true, then we can apply it to prove that conjecture, the first one, as soon as we prove that transversely projective foliations, which do not come from smaller dimensions, in the sense of being a pullback, they have this property. And that's what we can prove so far. We can prove that. We can prove, let's state a theorem. We can prove that transversely projective foliations with infinite birational transformation groups, after modding out this fixed part, the part that which fixes all leaves, are defined by closed algebraic one forms. Theorem. Lo Bianco. Rousseau. Self. And Touzet. And it says the following, that F be transversely projective foliation on projective manifold X if cardinality of Bf over B fix F is infinity, then F is defined by a closed algebraic one form. So, and if we further assume that the foliation, the leaves, the general leaf is not algebraic, then saying that a foliation is defined by a closed algebraic form is saying that the transverse dynamics is modeled over a finite extension of C+, and the action of phi of the birational transformation on this leaf space is compatible with that action. So it will be almost by homothesis. Okay? And so when should I stop? At 55? 56. So in the 20 minutes that I have, I would like to explain how one can prove this kind of result. And we have essentially two approaches to do it. I'll try to explain and compare both. And again, one of the unpleasant things by both arguments which I'm going to explain, that they somehow hide the dynamics. They ignore for most of the part the dynamics. Of course, we are in trouble because in the level of generality that we are looking at, we have nothing. We don't know if there are fixed points. Our maps are just birational. We are working on arbitrary dimension. And it seems hard to figure out a good dynamical approach, but of course it would be much more, it would be extremely interesting to have a dynamical approach to prove this kind of result or even the conjecture. But the way that we are approaching the problem, we essentially don't do something, we start with something very similar to what has been done in dimension 2. We use all the structure theorems that we have. Because we have strong structure theorems for this transversely projective foliations. So let me start to explain essentially the data that comes along with this object. So if I have a transversely projected foliation, as I explained, we have X, the base of the P1 bundle, which upstairs, I hope, yeah, right? So X is the base of P, and on X we also have the delta, the divisor. So this will be a divisor of tangent, the divisor on X, which essentially captures the tangencies, the invariant fibers of P. And since our foliation age is completely transverse to P outside this delta, we have a monodromy representation, which goes from the pi1 of X minus delta to automorphisms of P1. So this natural generalization of Poincaré first return map. It's the monodromy of this Riccati foliation, if you want, or we're just following the leaves of age to lift paths on X minus delta. And so delta is the singular point, singularities of. And the point is that these singularities of age come in two flavors. So we have, so this situation, this foliation age, is a projectivization, is locally. A projectivization of a flat meromorphic connection. And so the theory here is a local version, at least locally, is very close to the theory of linear differential equations, and we know that singularities come in two flavors. We have regular singularities, and we also have irregular singularities. So regular singularities essentially are defined by those which have moderate growth. The solutions have moderate growth when you approach the singular set along sectors, and irregular singularities when you have kind of exponential explosion of these solutions. Okay? And so to describe the structure of these transversely projective foliations is also describe the structure of representations of the fundamental group of quasi-projective varieties. And there is a beautiful result by Corlett and Simpson, which says the following. So if you have rho pi1 of X minus delta in PSL2C, or in SL2C, quasi-unipotent at infinity, and Zariski dense, then there exists a holomorphic map from X minus delta, or even algebraic map from X minus delta to the quotient of a polydisk by gamma, and this guy is of arithmetic origin. Such that rho factors through pi. So the representation of pi 1x minus delta will go through the representation of this guy, at least when it's seen as an orbifold. So this already poses a lot of restrictions on what this rho can be for our foliation. And essentially there are two problems. First of all, it's a result about representation, so it does not works well with the singularities, and also it has this assumption of quasi-unipotent at infinity, which is not satisfied at all by the objects that we are looking at. And so with Jorge and Touzet, we proved a version of these results. So it's a kind of a version of these results which works for transversely projective foliation. So in terms of the representation, we proved that if it's not quasi-unipotent at infinity, then, here we have an also factor for pre, or whole factors through an Orbi curve. And of course, when it factors through a curve, there's no reason for the representation to have arithmetic origin. Even if I can present a curve like that, it would not be arithmetic. And so if not quasi-unipotent at infinity, then rho factors through an Orbi curve. So this is just for representations. And if rho has irregular, or if H has irregular singularities, then conjecture, which I erased, holds. Then rho factors through an Orbi curve. Or H is defined by closed rational . So if you want, this is kind of evidence for this conjecture, and you can state this in the following way. Either the thing is Reilly structure, even if I'm doing a result for transversely projective foliation, so it's Reilly structure in a very, very strong sense. It's not only that it's transversely projective, but it's also that the monodromy representation comes from arithmetic and things are very rigid, or it comes from dimension 2. As soon as we have irregular singularities, anything like that, the things come from dimension 2, or is defined by a closed algebraic one form. Okay? So this is the one of the things that we use. And then we are reduced to, with these results, we are reduced to study this picture. So I have X, and here I have my foliation F, which I'm assuming transversely projective. And here I have a birational transformation preserving F. Or even I have the whole birational automorphism group of F. I know that this guy is transversely projective, So I have here this P1 bundle P, and I have this foliation H, and I have my section sigma. And essentially, we can prove that our phi, it's essentially by definitions, if you are in the case of intercept, this thing lifts here. And so let's say that we have a phi making everything commute, a big phi. And then we have this reduction. To a certain compactification of this guy. And we have also here this x delta. And here we have, let's call this z. We also have a z and a certain boundary. Let's call this. And from this Simpson result, in the case where it does not reduce to dimension 2, we have an induced map by phi here. And essentially what we want to prove in this situation is the finiteness of this map. And as I explained, we have two approaches, but both approaches rely on result by Brunebarbe, Cadorel, which refines previous work by Zuo and Brunebarbe, which says essentially the following, that this guy, if I write this guy, so here I'm putting Z, the open part, minus singularities, and delta is the boundary of this singularization, so the complement of this open part. And what they prove is that this pair is of log general type. So essentially, if we show that this action, the induced action of phi here, is compatible with the map, with the boundary, then you would get finiteness by old results of Itaka. And this is one approach. And essentially, to prove that, the key point is to prove the following. So if I take here on Z delta, I can take a curve, a map from a curve to here, such that the image of C is not contained in delta. And what we need to prove is that the representation, the restriction, the restriction of the map, the image of pi1 of C to pi1 orbifold of Z, so H over gamma, H over gamma, pi1 C minus some points, C bottom, is not solvable. So essentially, using that this image is not solvable, we are able to show that the action is compatible with this decomposition, and we can show that the action here, this will be injective, and then we get finiteness by means of this result of Itaka. Finish? So, and the other approach is essentially is to do the kind of, is in consonance with this conjecture, is that this recate, at the end we are not going to study like this, but we are going to study the foliation age. So you have to prove a reduction of singularities for the foliation age in order to be able to do the birational geometry and prove the invariance of plurigenera by means of action of birational maps. And again, using this general type of Z delta, we can provide another proof, an alternative proof of the finiteness of the birational transformations preserving pH, and then of the birational transformation per having XF. Okay, thank you.